Okay, so we are in our last lap on discussing about dynamics of turbulence. We say that turbulence is a continuum phenomena governed by Navier-Stokes equation. This is the most generic form for incompressible flow. We could have a time dependent body force, or it could be time independent. Even when it is time dependent, we noted yesterday very specifically that body force does not have fluctuating component. It is essentially an input, deterministic input. So, we will view it in that respect. Then of course, we perform this double decomposition of variable as was originally suggested by Reynolds, which involves splitting the variable into a time averaged part and a fluctuation. Time averaging is as defined here, done over a span of time from 0 to tau, and the tau going to infinity would perfectly define your time average. Okay. Now, the other fluctuating component, we very specifically say that it is truly random. This was the point of view adopted by Reynolds at the onset of all this studies way back in 1880s. Today, we have a slightly different point of view. We know that all these flows, although have fluctuating component, underlying it we have deterministic structure, and that is what we discussed about in POD. From a stochastic dynamical system, we tried to come out with some kind of background deterministic structure. So, this is debatable then, but then we will proceed, because most of our computing tool available today for turbulent flow is based on this assumption that the fluctuation is truly random. And we saw that along with this equation and with this kind of approach of defining the fluctuation as truly random, we can split the boundary conditions, put all the time independent boundary condition on the mean part that makes V or its any of its derivative to be satisfied by homogeneous boundary condition. Okay. And once we do that, we did derive in detail the governing equation for the mean quantity. So, what we did, we took the Navier-Stokes equation, we split this each of the variables into a mean part and a fluctuation, and then performed a time averaging over the whole equation. That led to this convective term for the mean. An additional stress term came about, which we called as the Reynolds stress, and this is one area of research which purports that we need some additional information, right. Per se, this equation is for the mean quantity. We do not have any sort of information a priori about the status of this, and what we figured that that to be able to solve this equation, we should have some kind of a model. That is what is called as a turbulence model. If we write down the equation for the mean quantity, similarly we can obtain the governing equation for the fluctuation, and the governing equation for the fluctuation would be given like this. So, what you do is you take the full Navier-Stokes equation, from there you subtract the mean equation, that will give you this. And what you see here, that this fluctuation is then governed by the status of the flow as given by the mean flow and also by the pressure gradient. This is one interesting aspect of incompressible flow, that you do not have an equation of state as such coming into play. What determines the dynamics is basically pressure gradient, not the pressure, right. So, this is one of the issue that we also have to keep in mind. And once we decide what this is, then we can sum it up that the time averaged or the stationary Navier-Stokes equation is what is called as a RANS or the Reynolds average Navier-Stokes equation, which requires modeling of this additional stress term for the fluctuation. So, we basically would like to comment theoretically what is the status of this additional stress term without specifically going into any particular model. Now, we could write down those governing equations also in the tensorial notation in this particular fashion, with the Cauchy equation written like this in terms of the stress. The stress itself was split into a mean and a fluctuating component, and that is what we write here. The stress itself has two components, the hydrostatic part given by the pressure and the total strain, total strain, rate of strain, which is defined here in terms of the velocity field. Once we have this, what we could do is, as I said, that we could split the total stress into a mean part and a fluctuation part. The mean part would come from the mean pressure, hydrostatic pressure, and the mean strain rate given by equation 9b, and the fluctuating stress could be written in terms of the fluctuating pressure and the fluctuating rate of strain. So, they are those given below, the strain rates are defined there. So, there is this alternative form of time averaged equation, which you could write it in this form. The convective acceleration is balanced by the stress gradient and the body force, and the stress itself is written in terms of the mean hydrostatic pressure and the part proportional to the mean strain rate and the Reynolds stress term. Now, we did talk about the fluctuating quantity, that it is driven by the mean flow and the pressure field. Body force does not come into play, neither would the boundary condition have any say on determining the turbulent fluctuation, and we need information about the Reynolds stress, and this would be interesting to note that if we want to write down a governing equation, dynamical equation for this stress, we see that that equation will involve a triple correlation term, and this is what we call as a turbulence closure problem, meaning thereby that at no level we should be able to close the system. Every system will have a higher order correlation term. And I also explained to you that people had been looking at it from a different perspective, with the hope that at some higher level this stress term, higher correlation, may drop off. That is what people have done experimentally, but not to much great success. The complementary aspect would be that you do not try to write down this equation and try to get the triple correlation, etc., but go downwards. You look at this and try to relate it with the mean strain rate. This is essentially what is done in most of the computations of turbulent flows, that we try to relate the mean stress mean strain rate with this Reynolds stress. To basically understand how we can do that, we need to understand the energy equation that defines the mean flow and the fluctuation quantities. When you look at the mean flow, these are the governing equations that we have seen beforehand, and to derive the energy equation for the mean flow, what we do is take a dot product of this equation with the velocity vector, and then we will get an equation for a quantity like this, half of u j times u j. So, that is your kind of kinetic energy, specific kinetic energy, and once you write that, take the dot product and write it down, you get this. What does it tell you? See, of course, we did this does not depend on time, but just for the sake of completeness, I could add a del del t of half ui times ui. So, then the left hand side will be what? The substantive derivative of the kinetic energy, specific kinetic energy. That is driven by this. Okay. What is this term? This is like your gradient transport, right? Because here j is repeated, so it is like del dot, the divergence term. There will be this additional term that will come about. We will see what it is. This is basically a stress, and this we can see it is related to the strain. So, there is a stress times strain that takes away the energy from the mean motion, and this is the work done due to the body force. Okay, so look at that term I told you that which involves the product of the stress times this velocity gradient. Since this stress tensor is symmetric, so this term we could just simply write it like this, right? Because what is Sij? Sij is half of this plus del u j del xi. So, when I take the product, they will be synonymous, right? So, this is what we are getting, and this is what we are noticing, that this is basically your transport of mean kinetic energy by Tij. That is what we are looking at in this equation. Okay, now, what we need to do is we could look at the energy over the whole domain, or we could look at it at a point wise, right. So, let us take a point of view of viewing the energy over the whole domain. Okay. So, basically it is all the 3-dimensional space that we integrate. What does this term give you? This is from your Gauss divergence theorem, right. So, this divergence term is nothing but the fluxes, those are coming in through the control surface. So, if this is done over the whole thing, so this is your control surface integral. Nj is nothing but the unit normal of this surface element, which area element which we have talked about as d2x. Okay. Now, you can observe that if you are taking a domain which is very, very large enough, you go very far away, then what happens is that this tau ij, the stress may vanish, right. If I go to the uniform flow path, the stress may vanish there, or we could look at the solid body where the stress is non-zero, but because of no slip condition, the velocity itself will vanish. So, in either of the case, whether you are looking at the solid boundary or the far field boundary, the right hand side will contribute to 0, right. So, when you are looking at this, then what you notice that that kinetic energy that is transported by Tij, if you sum it over the whole volume, it does not really the flow to other, but overall considered the whole volume, this does not do anything. This term, the other term that the second term on the right hand side relates to a product of stress times strain rate, right. This is what we are very familiar with. This is your deformation work, right. In elasticity we have studied that is what we get. Stress times strain is your deformation work. Okay. If there is no deformation, if there is no strain rate, then this term will be 0, right. So, it represents basically kinetic energy of the mean flow that is either lost or retrieved from the agencies that generate various stresses. So, what we could do is we could define the kinetic energy also in terms of a norm. Okay. These are definitions. So, do not have to worry too much about it. It is half rho u square integrated over the whole volume. We write it itself as half times rho and this. So, that defines your norm for the mean velocity field, and then we could write down the equation in this particular form. As I told you, we could add on this term without loss of any generality. Then what happens is this plus this will give you this total derivative, right. So, that is what we have written. So, that again we can perform the integral over the whole volume and define it in terms of the norm. Okay. So, this is basically the time rate of change of mean energy, that is what we are talking about. So, that would basically then come from this two component deformation work and the body force work, right. And we can take a closer look of what constitute this deformation work, right. I could write down the stress in terms of the hydrodynamic pressure, hydrostatic pressure, the mean strain rate and the Reynolds stress, and this is what that is then. Okay. So, basically then Tij Sij integrated over the volume will have these three components, and let us look at one of the component, namely the pressure term. How is this hydrostatic mean pressure relates to this Sij. Note that this has a delta Ij. So, if I am doing this, so this will only contribute from the trace of the rate of strain. So, only the diagonal element of the Sij matrix. So, that will be Sii. So, Sii is by definition is this, and what is this? This is this, and what is this? This is mass conservation equation for incompressible flow. This is 0. So, what happens? Then this quantity does not contribute. So, pressure does not contribute anything to deformation, and you can guess it also because it is hydrostatic pressure, it is isotropic. You can't create a strain rate. Why? You can only create a strain rate in what way? By changing the volume. But we are talking about incompressible flow. That is why this does not contribute. You saw that because it comes out from Sii. If we are looking at compressible flow, Sii is non-zero. Then of course, pressure will contribute to deformation work. But the moment you talk about incompressible flow, you exclude the possibility of any compression or dilatation, then of course, you would not get that. Note also that when we are looking at body force and consider that as conservative, if it is so, then we can write it as a gradient of a scalar, right, with a minus sign indicating it is conservative, right. So, if I do that, I could rewrite the dynamics of the overall quantity, the Navier-Stokes equation. So, instead of f, we have written minus this. So, what we could do is we could take this on this side, because we have two gradient term, one is due to the pressure, the other is due to the body force, and we can actually redefine an augmented pressure field which has the hydrodynamic part plus a contribution coming from the body force, and this is what we are going to get. And we have already shown that for incompressible flow, the pressure does not contribute to deformation work. So, having a conservative body force, that also would not contribute anything to deformation work, right. So, this is something we must understand. Then what we are left with is that rate of change of mean motion kinetic energy would be given in terms of two terms. What is this? This is your viscous deformation work, right. That is what your mu is, and Sij times Sij is a quadratic in the mean strain rate. and this is the work done due to the Reynolds stress. And this, of course, if we talk about non-conservative body force, it will also be there. So this is one of the way of writing out the total kinetic energy associated with the mean flow. We could also write it as a point property instead of integrating over the whole domain, and then we would be writing it like this. This is also something we understand. Once again, you notice what? This is that your gradient transport, right? So this is the divergence term. There is J here. So if we integrate over the whole volume, and if we can somehow show that this vanishes either on the solid boundary or on the far field boundary, this will not contribute. What then would contribute is from the mean strain rate and the eddy viscosity sort of term. Okay. So either of this form would be amenable in our discussion for mean motion, mean kinetic energy. Okay. Now we could turn our attention to kinetic energy of the fluctuation. We talked about the mean motion. Let us now talk about the kinetic energy of the fluctuation. Here we would be talking about the mean kinetic energy of the fluctuation given by half of Vi dot Vi, and this is the time averaged quantity. So we indicate it by the angular bracket. Now if I look at the Navier-Stokes equation and multiply it by Ui, that is basically taking a dot product to the velocity vector, and then we take the time average of the resultant equation, and from there we subtract the kinetic energy equation that we have written for the mean motion in the previous transparency, which we wrote it for a single point. So this equation is also written for a particular point. So from this equation is obtained by subtracting this mean part from the instantaneous. That gives you this. Okay. So this is what it is. This is what it is. So you find out that the turbulent energy budget, so it's we're calling it turbulent energy because it's associated to the fluctuation, and there we have this convecting term. We could also add a time dependent part of this stress, but please do understand that Reynolds stress term could be time dependent. It's not that it's a sort of a ornamental term which is identically equal to 0. Here it could be necessarily be there, and once again we have this three sets of terms. One of course is the gradient transport term, we can see it. The second one is what the Reynolds stress interacts with the mean strain rate, and what is this? This is due to the viscous dissipation. That is what it is, 2 mu times Sij times Sij. Sij, lowercase Sij stands for fluctuating strain rate, right. So that is what we are going to get. So if I then look at it, then the kinetic energy of fluctuation can be brought about by pressure term, pressure gradient term. Then we could talk about transport by turbulent velocity fluctuation, and transport by viscous stresses, and two types of deformation work. So let me just move back one step, and then this is what we are talking about. So we are talking about the pressure gradient term that is coming about, and this is that transport by turbulent fluctuation term, right, and this is your viscous losses, and these are two sets of deformation. One is due to the mean, other due to fluctuation. Okay, that's what we just catalogued it as a summation of 5 terms that come about. Okay. Now if I look at the transport term, that is the del xj of that whole quantity, they are nothing but divergence of a energy flux, right? That's what we have. So basically we are writing here is nothing but del del xj and some quantities which are this. So this is what we are talking about as the energy flux. Well, energy flux means we are talking about the fluctuating energy. Okay. So this is a divergence of this is your divergence operator. If this we are talking about the jth component, so that's what we are getting. So if I talk about this energy flux out of or into a closed control volume, this is going to be 0, because if I take a very large volume outside, again the fluctuation will go to 0 there. If I go far away from the physical body, on the body the fluctuations themselves are 0. So what happens is this term will not contribute if I integrate it over whole volume, right? So that is because you write it. So this is your volume integral, that you will write it as your area integral, and then you will be writing say Ng unit vector into that flux, that energy flux that you are writing there. And this will be this. And this quantity is going to be 0 on all the boundaries, whether you are looking at the solid boundary or the far-field boundary. So that's what we are saying, that contribution will be 0. This term only redistribute energy from one point of the flow to the other. The two sets of deformation work that we had, one corresponded to the Reynolds stress times the mean strain rate, right? Well, this basically tells you how this is getting created and where is it getting created from? From the mean field itself. So this is some kind of a production term. This is how turbulence is created. So energy is transported from the mean to the fluctuation field. And if you actually look at this term and a similar term in the mean motion, you will see they are of opposite sign. So whatever is lost to the mean motion is gained here in the fluctuation energy. So that's why we are writing this. We are seeing that what is happening. I mean, it's not like what we did in the study of instabilities. In the instability studies, we just presume that the disturbance growth occurs because there is always a unlimited source of energy from the mean. But here the disturbance quantity, the fluctuation quantities are of the same order of magnitude as the mean. So we'll have to look at it together, side by side. And that's what I'm suggesting, I'm showing it to you, that this kind of production term that we see in the kinetic energy of fluctuation, we get a same term but with opposite sign in the mean energy equation, right? So this is the same thing. So basically what we are getting is exchange of kinetic energy between mean and fluctuating quantities, and a gain for one is a loss for the other. So we could then finally focus upon the last term. The last term is this. This is nothing but 2 new kinematic viscosity times Sij times Si. This is truly the viscous deformation work and is a drain of energy. And what is it? This is a quadratic term. So it's always going to show you as a loss. So that's why we're calling it as a viscous dissipation. And I do not need to emphasize it again to you that this term, contribution coming from the fluctuating strain rate will be much more than the mean strain rate. Why? Because the fluctuating quantities are occurring over a smaller scale, so the rate of strain tensors are going to be predominantly stronger compared to the mean eddies. Mean eddies will be larger, fluctuating eddies will be smaller. So that's why don't think that this is a lower order term. In fact, it is a higher order term. And this is one of the reasons that turbulent flows are considered to be more dissipative than corresponding laminar flow because of the presence of this term, right? So this is something we must keep in mind. Now, what we are going to do is now we'll go over to the next part of our discussion. We have now been able to write down all the things that we wanted to. The turbulent energy budget is given by this equation. We just now seen this term. So this term is what we had written here, and this was a turbulence production term, and this is a viscous dissipation term, right? That's what we see when we look at the turbulent kinetic energy. So consider the case when this Reynolds stress is time dependent, then we can talk about this rate of change of that turbulent stress would have this local and a convective term, and that if we integrate over the whole volume, once again will help us in defining a norm for the fluctuating quantity, right? So this is the approach that we'll be taking, and then what we are going to get is the corresponding turbulent energy budget written over the whole control volume. Just now what we talked about was the point properties, but now we are integrating over the whole domain, and this is what we are going to get, right? This is essentially the same equation but integrated over the whole volume. So once we have that, then what we could do is we could talk about deriving the turbulent kinetic energy budget by looking at the corresponding equation written in a vectorial notation like this. This is what we derived it yesterday. So now if I take a dot product of this with respect to V, then we get the following equation. The following equation would have contributions coming like this. Okay. So there are two ways. Either we define our turbulent kinetic energy fluctuation in terms of this integrated version. This is equation 21, or the previous one, and we can talk about it. Now, if we go back and take a look at equation 19. Equation 19 was the following equation. Well, let's move over and see what that equation is. Yeah. Now, what we are talking about is the time rate of change of the turbulent energy fluctuation is given by this gradient transport, given by this production term and the dissipation term, right? Now let's talk about equilibrium turbulence. What do we mean by equilibrium turbulence? Let's understand it. Okay, so now if we are looking at the general flow, it looks like this. But let's look at a very special case. A special case where we are talking about a steady, homogeneous, pure shear flow. Steady in the sense we are talking about, of course, in the mean. Now, if we are talking about homogeneous pure shear flow, that by definition will imply that all the average quantities except ui are going to be independent of position, and in which Sij is constant. That is what we are talking about. So, Sij is not 0, but it is a constant, like a quick flow. We had the shear same everywhere, right. So, this is what we are talking about. We are talking about homogeneous pure shear flow. So, Sij is a constant. Now, then what will happen? If you look at that equation that we wrote, there were this gradient term that will not be there. We are talking about the steady state. So, the left hand side is 0. Then what is left is only the production term and the dissipation. So, for such a flow, that we have the kinetic energy of fluctuation equation looks like this. So, this is what we mean by equilibrium turbulent flow, right, where there is no net change. Whatever is produced is perfectly dissipated, equilibrium achieved, right. So, in most of the turbulence models that we see in existence, they originate from this concept that we have some kind of a production being kind of balanced by dissipation. And once you have that, you can talk about certain properties. So, what we have written there on the left hand side, we have written the turbulent production term, and the right hand side we have written the rate of viscous dissipation, and that itself is a statement of equilibrium condition. Whatever is produced is lost. So, thus when we go over from this very specific case of homogeneous pure shear flow to a general shear flow, well, we acknowledge that this equilibrium condition is not satisfied all the time. Nonetheless, when you look at the order of magnitude of production and dissipation, they are of the same order. They are of the same order of magnitude. And this observation is used in all turbulence models. This is the main thing. So, now the production term, of course, involves Sij. So, Sij, I could write it like this. It is like del capital U by del x. So, we are talking about the mean motion. So, if we define a velocity scale, which I called here as u cap, and L is the larger length scale, the mean motion scale, then Sij is going to be like this, right. And additionally, what we also said, that when it comes to turbulent flow, the fluctuation quantities are of the same order of magnitude of the mean quantities. So, in that respect, then what is the order of magnitude of the Reynolds stress? That is also of the order of u square. So, we make use of this order of magnitude analysis, and then we see what we get. Once we get that statement of equilibrium, production is equal to dissipation, will give us this. So, this is the dissipation term, we have kept it as it is, but the production term we have purposely altered here, because what we had here, we had V I Vj times Sij. So, Vi Vj is u square. So, that we could write it in terms of this, you had L into Sij. That is just sort of a simple rearrangement or manipulation. Once we do that, then what we see, that Sij times Sij, its time average, is given like this. Now, this itself I can see that nu can go downstairs. So, UL by nu will be the Reynolds number. Of course, that factor 2 has been observed in C1. So, what we are seeing is a very, very interesting observation that I already been emphasizing time and again, right, that if we are looking at turbulent flow, which is necessarily a very high Reynolds number flow, then what happens? The fluctuating strain rate, that time average is much, much larger compared to the mean strain rate. This is the origin for the way we can estimate this. Now, additionally also you note the dimension. What is the dimension of strain rate? So, the strain rate that we had written here this is this, right. So, what is the dimension? This is the velocity, this is length. So, it is going to be a dimension. So, rate of strain actually is nothing but inverse of a time scale. That is why, you know, vorticity also has the same feature, right. Vorticity also has the same kind of dimension, isn't it? So, what you see that in a sense turbulent flow then defines a whole host of time scales, depending on whether you are looking at the mean strain rate or the fluctuating strain rate. You get different types of time scale. And what you find that the time scales of the fluctuating quantities and the time scale of the mean quantities, they are significantly different, because that is what we saw in the previous slide, that Sij lowercase fluctuating quantity is Re times capital Sij. That means what? That means that that these time scales of the mean motion and the time scales of the fluctuations, they are widely separated. They are widely separated. And once again, this should tell you why people do unstudy Rand's equation. It eventually boils down to this fact that these time scales are so far apart that I could do two types of time averaging operation. One will be a very small time scale, those relates to turbulent fluctuations, or I could do a time average over the this thing. So, when I write Rand's equation, I am actually performing the time averaging over the small scales, and then I am following the larger time variation. That is what we do. And if these two things are so much far apart from each other in terms of the scales, there is a reason for one to believe that if I plot on this side omega and on this side, let us say, energy of omega, or I could write corresponding k, then what will happen is this sort of things will happen, that I have this part, the mean part and the fluctuating part, they are separated wide apart and they do not interact with each other directly. It comes through all those indirect route of cascading and stretching we talked about. So, that is precisely what we are talking about, that if we are looking at very large Reynolds number flow, these events are not tuned to the same band of frequency. One works there and the other resides on the other side. And this is what makes Reynolds averaging a worthwhile operation. Now, this also would give you a justification what happens to these types of motions? See, what happens is high frequencies associated with turbulent fluctuations are related to very small length scales. So that's what we are saying. We have very small scale of turbulence, and that is independent of the large mean motion, right? These small scale eddies are getting created because of all those nonlinear processes. They are smaller in size, so they could be assumed to be also isotropic. They all look similar, because you may have a fewer larger eddies, but by successive breaking down into smaller eddies, the smaller eddies at the lowest possible scale are going to represent a sort of a isotropic structure. This is what is called as a local isotropy assumption. So in all large eddy simulation, LES calculations that we talk about, we make this assumption. The flows are different in the large scale, but when you are looking at it at the lower scale, there the eddies have some kind of a universal feature. They are independent of rotation or reflection of the coordinate system, so that we can treat them as isotropic vortices. And then once that is done, you can say, well, if different flows have same small scale quantities, I could have a single model for this small scale events. And these are what are called as subgrid scale stresses. So please do understand that we are now looking at a different aspect, but essentially the ideas are related. Ideas are related because we have been now generally talking about the specific energy of the mean motion, specific energy of fluctuations, but what we see that when we write down the say Reynolds average equation, we talk in terms of time scales, and when we are talking about large eddy simulation, we are talking about its behavior from space variation, but they are somehow related because we see the dimension of Sij is 1 over t. So you see, this is a sort of an advantage, but if not done carefully, this can actually lead to confusion. So let's not worry about this, but now having done all of this, that we can talk about Reynolds stress or the subgrid scale stress, then life is a little more comfortable. You know what we are talking about in large eddy simulation? We are talking about computing in with some precision that at the level of local isotropy, we don't need anything because we have gathered theoretical information that it is isotropic. Okay? So I don't need to needlessly resolve the flow much finer. I can use that information garnered already and put it in there and solve for the larger eddies which are not isotropic, which are not homogeneous. That is the whole concept. Okay? Now, we still have not forgotten where we started. We wanted to relate the Reynolds stress with the mean strain rate. Right? So what happens? If we look at this equation 21, that was that turbulent fluctuation energy that we wrote in an integrated form over the whole volume. Now for that flow, if I assume equilibrium condition, that means I say the ddt of that quantity equal to 0, then the steady state would be reached, and what would we get? Well, let's go back and take a look at equation 21 for our convenience. Here it is. So we are talking about a steady state has been reached. So we are knocking off this quantity, and this is your capital Sij, and this is your Vi Vj, this is your production term, right? And that is your sort of loss with respect to the turbulent fluctuation. Okay. Now, if I go back and start talking about this, that this would then, if I time average that equation that I just now wrote, it will all come down to this term. Okay. So this is what we are getting, that del Vi del Xj times the Reynolds stress integrated over the whole volume should be equal to 0. If I say that, then what will happen? This is what is going to be retained. This is your production term, and this is your dissipation term. Again, stating the same equilibrium condition, right? This is always negative, implying dissipation, and this is your mean strain rate. So what is it? This quantity is negative, but non-zero. That means what? The mean strain rate and the Reynolds stress, when I integrate over the whole volume, they do not become equal to 0. If they were 0, if the result is 0, then what do we conclude? That these two quantities are not correlated over the whole domain. However, what we are noticing is, indeed they are correlated, and the correlation is a negative correlation. Okay. So this is the reason that we always try to relate the turbulent stresses with the mean strain rate. This is the mainstay of most of the turbulence models which have been proposed ever since the term of Prandtl. Okay. So you understand all those algebraic models came about just from the simple observation of equilibrium turbulence, that the mean strain rate is negatively correlated to the Reynolds stress. And on this note, we'll stop today.